So, let us have some interactive problem solving sessions by students who have taken this course. So, you will see some illustrations and examples into problem solving which is useful to understand and digest the concepts learnt during the lectures.
I am Chaitanya, a PhD student at IIC. So, today we are going to look into a problem that discusses the signal classification. So, we have studied signal geometry in the class. So, we are going to apply it for some kind of a practical example. So, here we have a source that transmits one of the 4 signals S1, S2, S3 or S4. So, it transmits one at a time where each signal Si is given by a cos signal cos 2 pi t, but shifted by different phases. So, the first signal is offsetted by pi by 4 offset, the second one by 3 pi by 4, third one by 5 pi by 4 and fourth one by 7 pi by 4. So, and each of these probability signals are transmitted with certain probability either 0.1, 0.2, 0.3 or 0.4 respectively. So, the question here we have is, so we have these signals and the question asks us to represent these signals using appropriate basis in a signal space. And the second question, second part of the question, it asks us to identify the regions within the signal space in order to make a proper classification of the signal. So, we will get into the details of this question. So, for part 1, so notice that the signal root 2 cos 2 pi t minus theta I and theta I, they belong to pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So, these signals, these are called quadrature phase shift keying signals. Or QPSK. So, we can actually expand this cos term as theta as this root 2 cos 2 pi t cos theta I plus sin 2 pi t times sin theta I. So, this root 2 is missing. So, this can this cos theta and sin theta I, they are dependent on the signal I. So, this can be written as AI cos 2 pi t plus BI sin 2 pi t, where the coordinates AI comma BI, depending on the phase shifts, we can write them as 1 comma 1, or I would say A1 comma B1 as 1 comma 1, A2 comma B2 is minus 1 comma 1, A3 B3 is minus 1 comma minus 1, A4 comma B4 is 1 comma minus 1. And if you notice, this signal is written as a summation of 2 orthogonal signals cos 2 pi t, linear combination of 2 orthogonal signals cos 2 pi t and sin 2 pi t. And in fact, you can easily verify that cos 2 pi t and sin 2 pi t are normal signals also, that is the energy in each of those signals is 1. So, essentially here we have the basis. Basis is nothing but this 2 cos 2 pi t and sin 2 pi t, and these form the signal points. I can call them as S1, S2, S3, S4. So, these 4 forms the points in the signal space. So, in order to visualize what it means, here we have sin 2 pi t, cos 2 pi t, we have S1 equal to 1 comma 1, S2 is minus 1 comma 1, S3 is minus 1 comma minus 1, and S4 is 1 comma minus 1. So, this represents the signal space that we have. Signal space, and the signal the 4 signals S1, S2, S3, S4, they are represented as points in this particular signal space. So, now moving to a quick comment. So, here this particular form is called quadrature amplitude modulation. Here we have 4 points, so it is called 4 QAM. So, now moving to the part 2. So, with noise, so with noise the received signal you can write. So, if x comma y are the values, they are going to be of the form a I plus n x or comma b I plus n y, where n x and n y are Gaussian noise samples with 0 comma sigma square, 0 mean and variance sigma square. So, essentially what it means is we have these 4 signals S1, S4, however, because of this noise, each coordinate there is going to be some noise that gets added. So, the actual received samples will not fall exactly at these places, but it could be anywhere outside. So, it could be distributed somewhat like this. So, if we plot all these received samples, it forms a constellation like this, centered around these individual points S1, S2, S3 and S4. So, for optimal detection what we need to do is we need to maximize a posteriori probability. So, this is the criteria that we choose. So, we need to so essentially we want to identify a signal Si for which its a posteriori probability given by probability of Si given the signal which is given by probability that using Bayes theorem we write it as probability of S given Si times probability times Si by the probability of S is maximized. So, what it essentially means is we have received a signal S and we want to maximize this a posteriori probability for different choices of I and see which signal maximizes this a posteriori probability, and that that signal is the decision that we will make. So, that is the optimal decision. So, essentially because the denominator is same for all i's, we want to maximize probability of S given Si times probability of Si is maximized. So, we know here in order to compute these we have probability of Si equal to Pi, the values are given, and in order to compute this probability of S, this other term, so we just expand it. So, probability of S given Si is nothing but probability that x is ai plus nx, comma y is bi plus ny. So, which we can write it as probability that the noise sample nx is nothing but x minus ai, and the noise sample in the y coordinate is nothing but y minus bi. And we know this it was given that these noise samples nx and ny are independent. So, we can write them as probability of nx probability nx equal to x minus ai times probability ny equal to y minus bi, and using the Gaussian distribution we can just write them as 2 pi e power minus x minus ai squared by 2 sigma square times e power minus y minus bi squared by 2 sigma square. So, this gives us the terms that we that are involved in computing this a posteriori probabilities and towards making the decisions. So, now consider the decision boundary between two signals. So, the decision boundary or let us say we call the decision region. So, the decision region for the signal, let us say we pick S1, a particular signal S1 is where this probability that we have written down earlier times probability that S1 is greater than the same probability for any other signal Si. For all so, whenever these conditions hold true for all I equal to 2, 3 and 4, we say that the received signal S is very we make a decision that the received signal S is based on the signal S1. So, similarly we can extend it for other signals, this definition S2, S3 and S4. So, now based on this inequality that we have, we can define a decision boundary between two signals. So, essentially this Bij of x y, it forms a decision boundary which is given by, so I say Bij equal to 0 is a boundary between between the signals Sij and Si and Sj regions, which is given by Bij x comma y, which is nothing but I just take the difference between these two terms, probability times Si minus probability S probability Sj. And looking at this, we can easily say that Bij of x comma y is minus of Bji of x comma y. So, this is for all I not equal to j. So, what this essentially means is the decision region for the signal S1 is the intersection of all these sets or all these spaces B 1 2 x comma y greater than or equal to 0, or I will just stick to the strict inequality, intersection x comma y B 1 3 is greater than 0, intersection x comma y B 1 4 x comma y is greater than 0. So, this is essentially the decision region for the signal S1. Similarly, we can define the decision region for S2, S3 and S4. It is going to be in the similar form where it is going to be intersection of 3 sets. Now, to conclude this part, we have to compute these decision boundaries. So, let us look at this condition Bij x comma y is greater than 0. So, I compute these terms, or I substitute these terms from our earlier derivations. So, we have 1 by root 2 pi e power minus x minus a I whole square by 2 sigma square times 1 by root 2 pi e power minus y minus b I whole square by 2 sigma square times probability of S I is p I minus the similar terms for S j e power minus x minus a j whole square by 2 sigma square times 1 by root 2 pi e power minus y minus b j whole square by 2 sigma square is times p 2 is greater than 0, or I will just say this. So, take log. So, what we on both sides. So, what we get is so these terms cancel out here, and p I instead of p 2 it is p j. And taking logarithms, we have minus x minus a I whole square by 2 sigma square minus y minus b I whole square by 2 sigma square is greater than logarithm of p j by p I minus x minus a j whole square by 2 sigma square minus y minus b j whole square by 2 sigma square. So, this further can be written as half of x minus a j whole square minus half of x minus a I whole square. So, I am just rearranging these terms and multiply both the sides by 2 sigma squares plus half of y minus b j whole square minus half of y minus b I whole square is greater than sigma square log p I by p j. So, this is what we have, and further simplifying. So, also note that a square is same as a j square equal to 1. Similarly, b I square equal to b j square equal to 1, because a I and a j are either plus or minus 1. So, certain all these terms aj square, ai square, bj square, bi square and x square from both these terms. So, all of them get cancelled out and you will be left with a linear equation which will be of the form x times ai minus aj by 2 plus y times bi minus bj by 2 is greater than or equal to sigma square by 2 logarithm of pj by pi. So, this is nothing but bij of x comma y greater than or equal to 0. So, this is the decision boundary between the signal I and j. So, we will just substitute these points. So, for that I mean to demonstrate that I brought this graph paper. So, we have the signals S1, S2, S3 and S4. So, let us look at each individual boundaries. So, if we look at B, if we look at the boundary B1 2 of x comma y greater than or equal to 0, this is given by. So, between the signal 1 and 2 the only x coordinate changes and y coordinates are the same. So, essentially bi and bj are b1 and b2 are the same, but a1 and a2 are different and hence we will be left with just the term x is greater than sigma square by 2 ln p2 is 0.2 by 0.1 and let us assume sigma square equal to 1. So, we will use this for the convenience of plotting. So, this comes out to 0.3466. Similarly, we compute the boundary between 1 3 implies. So, here a1 and a2 a3 are different and b1 and b3 are also different. So, we will have both x and y terms is greater than or equal to sigma square by 2 ln 0.3 by 0.1. So, this comes out to 0.5493 b14 x comma y. So, between 1 and 4 only the b1 and b4 are different, a1 and a4 are going to be the same. So, we will have only the y term is greater than sigma square by 2 ln 0.4 by 0.1. This comes out to 0.6931. So, I am just taking these values so that I can plot here and show you. And we know that B21 is same as B12 with a negative sign and B23 x comma y. Similarly, following the same procedure, we have between 2 and 3 only the y coordinate is different. So, here we have y is greater than sigma square by 2 logarithm of the ratio of probabilities, which is 0.3 by 0.2 and this comes out to 0.2027. Similarly, B24 between 2 and 4 both x and y coordinates are different and if you substitute you will get this. And for 3 1 we know it is b negative of b13 and between 3 and 2 it is negative of b23 and b34. So, between 3 and 4 it is only the x coordinate that is different. So, you will have minus x greater than or equal to sigma square by 2 logarithm of 0.4 by 0.3, which is 0.1438, and for 4 it can be computed from the remaining boundaries. So, we have 4 1 is minus b 1 4, b 4 2 is minus b 2 4, b 4 3 is minus b 3 4. So, all these terms are already computed here, all these boundaries. So, let us plot these boundaries one by one individually. So, I will use a different color. So, let us look at b 1 2. So, b 1 2 is x greater than or equal to 0.34 or x equal to 0.3466. So, the boundary looks like this, b 1 2. Similarly, let us look at b 1 3, x plus y is 0.5493. So, the boundary is going to look like this, and b 1 4 is y greater than or equal to 0.6931. So, these are the boundaries that we have, and we classify the signal as S1 when it lies within the intersection of all these boundaries. So, essentially it is this region. So, for that what I will do is, essentially it is this region. Let me remove the unnecessary boundaries that are not in use. So, this is the decision region for S1. So, let me shade it a bit. So, this is the decision region for S1. Now, similarly for we can continue this for S2. So, between 1 and 2 we have this boundary that is already present, and between 2 and 3, so we have it is greater than 0.2027. So, it is going to look like this, and between 2 and 4 it is minus x plus y is 0.3466. It is going to look something like this, and the intersection of all these regions is going to be this. So, let me and some of the other boundaries, they are not necessary. So, I will just erase these extra portions of the boundaries. So, this red portion that gives the decision boundary for S2. So, this is for S2. Similarly, for S3 I will use a different color. So, between S2 and S3 we already have this boundary. Between S3 and S1 we have a boundary which goes like this, and between S3 and S4, so the decision boundary is 0.1438. So, it is minus x is greater than or equal to 0.1438. So, it is going to look like this. So, now the intersection of all these regions is essentially this. So, let me remove the unnecessary boundaries that we saw. Yeah. So, this is the decision region for S3. And remaining space is the decision region for S4. So, this gives the decision boundaries for various signals S1, S2 and S3 and S4 within the signal space that we have seen. So, yeah, thank you.